So right now I'm just waiting until like 5 minutes have passed, so more people can join in. So right now So what motivated me to start and continue CP? Well, the problems are really interesting for me, and I really enjoyed the contest, so that's why I enjoy competitive programming a lot. I think that it depends on how many hours per day the person spends on competitive programming. For me, even though I only took a few years, I spent like a lot of time. I spent all my time during the summers doing competitive programming. So, yeah. I have been programming for 10 years and for competitive programming specifically, it has been 2 to 3 years. To improve at dynamic programming problems, you really just need to do a lot of them. Yeah, I'm a high school student right now, and I'm about to go to college. So the best coding platform, I think it would be Codeforces, but then you would still have to use a lot of different types of coding platforms to get yourself, because each coding platform has their own problems, and getting to know all of the different types of problems is good for you. I will be going over both Div 1 and Div 2 problems today. But for the easier Division 2 problems, I'll just go over them briefly. Today's contest, I think it looks pretty unbalanced to me. So like, the second problem has 1,000 and something solves, and then the third problem in Division 2 only has 50 solves. And then in Division 1, it seems okay. Like, the difficulty for Division 1, I think it's just fine. Okay, so now it's 40, so I'm just going to start with the first problem. And the first problem is, what is this? So basically, let's look at the minimum elemented array, and that's called x. And then we realize that in our coordinate plane, in our axis, we start at 0. Then if we only have x, then we'll jump to x. And then we'll jump to 2x. And so on. So we know that the answer is smaller than or equal to x. But then the first jump over here that's exactly x. So it turns out that the minimum of the array A in this problem will be the answer. So in my code over here, I just input the array and find the minimum of it, and I output it. So yeah, this is pretty simple, and I think yeah, nobody should have any problems with it, so I'll just leave my code here and move on to the next problem. So the second problem. Okay, so the problem tells us that we have to find the number of p such that a modulo p is congruent to b modulo p. And if we subtract b on both sides, we end up with a minus b modulo p is congruent to 0. And this means that p is a factor of the absolute value of a minus b. So the first thing is, if a is equal to b, then the number of possible values of p is infinity. Then if it's not, then we can just factor this value. And the number of factors will be the number of possible values of p. So in my code over here, I basically find the absolute value of a minus b first. And if it happens to be 0, then I just return that there are an infinite number of solutions. Otherwise, I just run the factoring algorithm for this number. Then the answer will be the number of factors. So, see if anyone has any questions. And if nobody has any questions for this problem, then I'm going to move on. Okay. And the next one is range add. So for this problem, we need to find the summation, which consists of bitwise AND operations. And when we see this, we should think of counting the bits individually. So basically you want to count the answer for each bit. So for each bit, 2 to the ith power. So actually it'll be more convenient if I write it as 2 to the x. So then we need to count for how many I will the sum, for how many I will this expression contain the bit 2 to the x. And so we can do some casework here. So if L does not have 2 to the x, then the number of I is equal to 0. Otherwise, let L2 so otherwise L will look like this. So in its binary representation, it might look like this, where this is 2 to the x. So then look at L plus 1, and looks like this. You go all the way to some value L2 minus 1, and L2 minus 1, and from L to L2 minus 1, the bit 2 to the x always appears. But then for L2, it becomes 0. So now we need to find what L2 is. And we can do this. First, we we take the floor of the division of L and 2 to the x, and then we add 1 to it. So basically the floor of L divided by 2 to the x looks like the top part over here. So if we want to change this bit over here, then we need to add 1 to this bit over here, so that this part of L becomes this. So then this bit will be the first one to be 0. And then we need to add these zeros back. So we multiply the entire thing by 2 to the x. So then the number of I will be L2 minus L. Then we add L2 minus L times 2 to the x to the total answer. So in my code over here, we basically iterate over all of the possible 60 bits. And then, so for the first part, this if statement checks if 2 to the I, if the bit I is part of L. And if the bit I is not part of L, then it basically skips this bit. Otherwise, we find L2 using the procedure that I just described. And then also remember we have to take the minimum of this and r plus 1. So after we find L2, we just add the number of I and multiply it by the value of the bit. And we add it to our answer. So I'm going to send my code, which is here. So are there any questions of what I just explained for the problem range add? And yes, I will save this stream on my channel so people can watch later. So if there are no questions, then I'm going to move on to the next problem. So the next problem is CHFINA and sums. So basically, you want to iterate over k, and then want to see how many ways, and then first we iterate over k. Then we find the sum of a single partition. So basically, the sum of the single partition will be, because the two partitions need to have equal sums, so we know that the sum will be equal to the sum of all values of a minus a of k divided by 2. So, and first we need to check that this is divisible by 2. If it's not divisible by 2, then this k doesn't work. So after we find the sum of a single partition, we need to find number of prefixes with sum x. And then we're going to call this x. So basically, if we have a prefix with sum x, then that means that the suffix will also have a sum x. So if we choose the prefix and the suffix, then that means we will find a way to split the sequence into 2 subarrays. So for example, for the first test case over here, So for k equals to 1, find that x will be equal to 4. Actually, I should write this out. So for k equals to 1, x will be equal to sum of a minus a of 1 divided by 2, which is 9 minus 1 divided by 2, which is 4. So we know that our prefix needs to have a sum of 4. So instead of finding a prefix, you can find a suffix which has a sum of 4 if it's easier for us. So our array looks like this, and the only suffix with a sum of 4 is this suffix. So if we split the array here, then we can satisfy the condition. So f of k is equal to 1. Then if f of 1 is equal to 1, and when k equals to 2, we can calculate x again to be sum of a minus a of 2 divided by 2, which is 9 minus 2 divided by 2. But then this thing is not even, so which means that partition is not possible here. So f of 2 is 0. Then f of 3. So again, we calculate x. And it turns out to be 4. Okay, and since our array looks like this, we need to find the number of prefixes or suffixes with sum equal to 4. I can find one over here. So this is the valid partition for k equals to 3. So f of 3 is equal to 1. And then for k equals to 4, you also find that x is equal to 4. And this time the array looks like this. And this time actually we have two different ways of partitioning the array. We can partition it with the prefix from a prefix from the left of 0, or we can partition it from a suffix from the right of 0, like this. So we find that f of 4 is equal to 2. So basically what we do is in our code, we need to use a map to store the number of prefix sums with a particular value. And you also do the same for suffix sums. So in my code here, first I calculate the total sum of all the elements in the array. And then first I calculate the answer for the prefix sums. So as mentioned earlier, I just fixed the element to be removed, and if the total sum minus the element is divisible by 0, then I calculate the sum that the prefix should have, and then I add the number of prefixes with this sum to the answer. Then I update the sum of the current prefix, and I add this prefix to the map so we can query it in the future. And I basically do the same thing for the suffix. And then one person told me that if you use a map instead of an unordered map, then you could get TLE, and this is because if you look at the constraints, so t times n can be up to 2 times 10 to the 6. So, and if you use a map is n log n. So 2 times 10 to the 6 log 2 times 10 to the 6 is, well, not 2 times 10 to the 6, but 2 times 10 to the 5. This is a bit risky and it might TLE. Instead, an ordered map will be O of n time. So it works faster in practice. Okay, if there are no questions, then I'll move on to the other problems. And if you still have questions for some of the previous problems, then you can stay after I finish going over the other problems. Maximum number of partition might be greater than 1 or 2, because if you look at the constraints, we could have negative numbers. So, for example, if we had a test case like this, then we can split it like this. You can split it like this as well. And we can also split it up like this. So, yeah, okay. So now I'll move on to the next problem, which is profitable paths. So in this problem, you should count for each node U how many paths go through U. So let's call this number equal to S2 of U. So once we have this number, we should greedily assign the larger values of S2 of U to larger values of A in order to maximize the total sum. And this is true because of this is intuitive, but if you don't notice, then this is called the rearrangement inequality. So this can be used to prove the greedy solution to this problem. Yes, so we calculate the contribution for each node in the tree. So in order to count this, count the contribution, we need to find for each subtree U how many leaves are in the subtree of U, and we'll call this S of U. And this S of U can be found with a simple DFS. So after we find S of U, we need to find S2 of U. So in order to do this, we can use complementary counting. So let's say we have our node U here, and then we have our children V1, V2, V3. Then U might be connected to some parent. So want to count how many unordered pairs of leaves do not go through U. So in order to count that, if a pair of leaves does not go through U, it means that it must be from the same subtree. So the number of pairs of leaves which do not go through U is the number of leaves in this subtree squared plus the number of leaves in the second subtree squared plus and you add this for all the children of U. But then you also have the parent. So in the parent subtree, you need to add the parent subtree has a total of the number of leaves in the parent subtree is equal to the total number of leaves in the tree minus the number of leaves in the subtree of U. So which means that we need to calculate this thing squared. Okay, so this sum that we found is the number of pairs of leaves which do not go through U. Now in order to find the number of pairs of leaves which do go through U, we just have to basically just have to calculate the total number of pairs, which is total leaves squared, and then we subtract this entire thing here, and then this will give us the number of pairs of leaves which go through U. And then since you want unordered pairs, we should divide this by 2, and that will give us the contribution of each node. Now once we have the contribution for each node, as I said earlier, we just need to sort the array S2. Then we also basically sort the array S2, and then we sort the array A, and then we greedily match the smallest A with the smallest S2, and then we multiply them pair by pair, and then we add it up to get the answer. And then this code is for finding the number of leaves in a tree. In my DFS, as I said earlier, S of U is the total number of leaves in a subtree. Then S2 of U, we calculate it using the formula that I just described. So yeah, that's pretty much it for this problem. So yeah, since the tree is not rooted, so we need to, so basically if you look at this sample case over here, it gives you an example where if you root the tree at 1, 1 is still considered as a leaf because it is a pair in the answer. So even if a pair is a root, if the root has a degree 1, then that means that the root is also a leaf. And then yeah, you could also do it like this. So because n squared and n choose 2, which is equal to n times n minus 1 divided by 2 are similar. So both of these can work. So if there are no more questions, then I'm going to move on to the last two problems. Okay, so next problem, which is almost palindromic, is in division 1 only. So, okay. So basically, if you look at the problem, first you can split the problem into, it wants us to find the number of strings, the number of numbers from L to R. Instead, we can calculate the number from 1 to R minus the number from 1 to L minus 1. And this will help us when solving the problem. So from now on, we'll just assume that the problem is just to find the number from 1 to R. Okay, so first we need to take care of the numbers with length smaller than the length of R. So to do this, first we need a dynamic programming, and dpij means that we need number of numbers with length equal to I and number of odd occurrences equal to j. So in order to update this dp, So first, basically you can choose, if we choose to use a number which has an odd number of occurrences, then we have j ways to choose that number, and after we choose it, we are left with a sequence of length I-1 with j-1 numbers, with j-1 digits with an odd occurrence. If we choose a number which has an even occurrence, then we have 10 minus j ways to choose that number, and after we choose that number, we are left with a sequence with I-1 digits, and there are j+1 digits which have an odd occurrence. So using this DP, we can find a lot of the answers to parts of this problem. So now we will iterate over I from 1 to the length of R. So for all of these numbers, we can start with a digit from 1 all the way to 9. And after we choose a number like this, we have a number with an odd occurrence, which is the first number, and then we are left with a sequence of length I-1. So dp2 of I will be the number, so dp2 of I is the number of numbers with length equal to I and are almost palindromic. So that's the first step of our problem. So the first step, we count the numbers with length smaller than the length of R. So what we do is we iterate over the length and we add the dp2 for each length as described earlier. So after we do this, we need to count. So what's left is to count the numbers with length equal to the length of R. And then to do this, we can use a standard digit DP procedure. So basically, for example, if the number we're working with is 2020, then what we do is we first count the numbers which start at 1, and these 3 can be any digits. And then after we do that, we assume that the first digit is 2. Then we move on to the next digit, and the next digit is 0, so we simply move on. And for this, we can assume that the next digit is 2 as well. Then we can add whatever digit is here, and we can use our DP to find this digit, to find the number of ways to fill in the remaining digit efficiently. So after we put 0 there, we put 1 here, and we do the same thing. And after that, we put 2 here, and then since 2 is equal to 2, we move on to the next digit, which is 0, and then we are basically finished. So there are a lot of details in this problem, and it's really hard for me to get through all of them in a short amount of time. So I'll just post my code here. And so, as I said earlier, map is O of n log n, while unordered map is O of n. And then for finding S2 of I, n choose 2 and n squared will give different. And okay, so n choose 2 and choose 2. And so I meant that it's n log n for n operations. So it's also log n for each operation. Also, n choose 2 and n squared are similar because n choose 2 is n squared minus n divided by 2. They both have n squared, and I can just divide by 2. I can just subtract n and divide by 2 to get n squared. Okay, so yeah, I forgot to change this the entire time. Anyways. So last problem is CNTIT. So basically, we're given this condition where the number of edges, the number of occurrences for a particular color, the multiset of the number of occurrences has to be polygonable. And this basically means that the maximum of S of I has to be smaller than or equal to the sum of all of the S. So for this problem, you can also use complementary counting. So you should count for each k number of paths such that S of k is greater than the sum of all of the other S. And then we can change this inequality into the sum of all the other S minus S of k has to be smaller than 0. So you want to count the number of paths such that this is true. And we can use centroid decomposition for this problem. So basically, if this is our centroid and we have a lot of other subtrees here, now what we do is we find all the number of paths which cross through this centroid. Then after we count the paths which cross through the centroid, we remove the centroid, and then we solve it individually for the subproblems. So how can we solve it for the centroid? So basically, for each subtree, we need to calculate the sum of, this value. So for each node v in here, you have to calculate the value for v to c. And after we calculate this value, we can use a binary index tree to combine the results for all of the subtrees. So for example, if we just have this tree over here, and you find that the path over here gives a value of -3, and actually, so there are more nodes here. Find that the path over here is -3, and we find that the path here is 2. So then, if we add them up, then we get a value which is smaller than 0. So we should count this path. And then basically, we can put all of these paths in a data structure such as a binary index tree. Then we can iterate through all of these paths again to query the number of pairs, which will give a sum which is smaller than 0. And again, there are complicated details in this problem which is hard to go over. So I'm just going to put the code. Okay, so these are both div 1 and 2 problems, and they have some overlap, but I just went through all of them. And if anyone has any other questions, I'll answer them. Oh, okay, so for CHFINA and sums, let me find the problem. Okay, here. So it doesn't just say subsequence. It says contiguous subsequence, which actually means subarray. So if we split a sequence into 2 subarrays, that means that one has to be the prefix and another has to be the suffix. On these problems, I guess they're at most Division 1 C problems on Codeforces, I would think, for this contest. Oh, okay. The concept of bits is actually part of a larger concept, which is counting with contribution, which actually appeared in 2 problems in this contest, in both CHFINA and SUMS, and also in the other problem, range add. So I think I might consider making a video explaining the contribution technique, which explains the contribution of bits. So and for DP problems, I can't really describe the approach, but basically, yeah, it's very hard to describe, but basically if you solve more DP problems, then you'll gradually improve. So yeah, that's all I can really say. Hi, what's up? Wait, to find good DP problems, I think there are a lot of... So first, you can use the filter by tags feature on Codeforces. And yeah, I think just going on Codeforces and filtering by the tags will help you a lot. Yes, it is 3:30 a.m. over here, but like a lot of the contests are at midnight anyway, so like I'm used to staying up this late. I usually sleep during the afternoon to prepare myself for midnight contests. Okay, I think the questions are becoming a bit off topic right now. So the questions are becoming a bit off topic right now, so I'm just gonna go off right now. I think you should, if this is your first contest, then it's pretty common for it happens to a lot of people. So for a lot of people, they don't solve any problems for their first few contests. And they basically improve in that practice section. So basically just do practice problems. Okay.